Today we have two speakers who will each present for about 20 minutes each, and then we'll go into a 20-minute question and answer session. Delegates can ask questions during the webinar by using the questions box on their screens. Send your questions as early in the webinar as you can, as then I can forward them to those speakers in good time. If your question is not answered during the webinar, please do submit it to our forum and we'll address it there. We'll provide the link to the forum at the end of the webinar. If you experience any technical problems during the webinar, you can also use the question box to send a query to my colleague Lorna, who should be able to assist. Delegates should also know that a recording of this webinar, along with all the slides, will be available on the Chemical Watch and the PETA International Science Consortium websites in the next few days. Now let me hand over to Gilly, who will provide some information on this webinar series and introduce you to the speakers.
Thank you, Philip. I'd like to welcome all the participants to today's webinar on behalf of the PETA International Science Consortium and to thank Chemical Watch for their support in hosting these webinars. The goal of this 6-part webinar series is to help registrants plan for the 2018 REACH deadline. Hundreds of thousands of animals have already been used for REACH testing, and millions more are expected to be used in the coming years. However, there are alternative methods that can be used to meet REACH data requirements while minimizing animal testing. For more information on minimizing animal testing for REACH, after the webinar you can go to our website where you'll find a page dedicated to promoting alternative methods. And also on our website you'll find recordings of all the past webinars in this series. I'd also like to let you know that our scientists are available to assist registrants in avoiding animal testing, so please feel free to get in touch if you have any questions. Today we are presenting the 3rd webinar in our series, which is focused on alternative methods for serious eye damage and eye irritation testing. Our speakers are Drs. Kim Norman and João Barroso. Dr. Norman works as a toxicologist at the Institute for In Vitro Sciences, a non-profit research and testing laboratory dedicated to the advancement of in vitro methods. Dr. Barroso works as a scientific officer at the European Union Reference Laboratory for Alternative Animal Testing of the European Commission Joint Research Centre. This organisation promotes the scientific and regulatory acceptance of alternative methods. During the webinar, Drs. Norman and Barroso will first discuss the drivers of in vivo classification for serious eye damage and eye irritation in order to define what is required to achieve full replacement of the animal test. Then the available in vitro methods and how they can be used either alone or in a testing strategy will be described. With that, I'll hand over to João to start.
Thank you, Gilly. Hello, everyone. So I would like first to thank PETA International Science Consortium and Chemical Watch for organizing this series of webinars and for giving Kim and I the opportunity to provide you an overview of the available alternative methods for serious eye damage and eye irritation and how these may be used to satisfy REACH information requirements. So here you can see the outline of our talk today. I will start by explaining the traditional regulatory in vivo Draize rabbit eye test and present you an analysis of a large set of historical in vivo data that was recently published to support acceptance of alternative methods and identify existing gaps that may still need to be addressed. I will then explain the current accepted framework for fully replacing the in vivo test, and I will hand over to Kim for her to present you in some detail the currently available alternative methods. I will then finish this presentation by explaining how these methods may be used under REACH and how they may be combined in testing strategies where needed to replace the animal test. Next slide, please. So, 4 different endpoints are addressed in the in vivo Draize rabbit eye test, namely corneal opacity, iritis, conjunctival redness, and conjunctival chronosis. Each of these endpoints is independently scored in every treated animal for a period of up to 21 days. The average scores of days 1, 2, and 3 in every animal are then calculated and used to decide on the classification of the tested chemical. The persistence of effects at day 21 is also monitored and used to distinguish between reversible and irreversible effects, with the latter being classified as seriously damaging the eye. Next slide, please. This table shows the UNGHS and UCLP classification criteria used in the Draize rabbit eye test. A chemical does not require classification and labeling according to UNGHS if, in the majority of the tested animals, the corneal opacity and iritis mean scores are lower than 1, and the conjunctival redness and chemosis mean scores are lower than 2. If the majority of the animals have mean scores for any of these endpoints above these cutoffs, and all effects are fully reversible by day 21, the chemical is classified as category 2. The persistence or reversibility of effects at day 7 may be used to distinguish between optional categories 2A for eye irritants and 2B for mild eye irritants. But these optional categories have not been adopted by EU in the CLP regulation and are therefore not applicable to REACH. Finally, if in the majority of the animals the corneal opacity mean scores are equal or higher than 3, or the iritis mean scores are higher than 1.5, the chemical is classified as category 1. A substance is also classified as category 1 if any of the observed effects persists until day 21 in any of the animals, or if a corneal opacity score 4 is noted in any rabbit at any observation time. These two criteria apply independently of the severity of scores obtained in the first 3 observation days. Next slide, please. For more than 20 years, scientists have been trying to replace the in vivo Draize eye test with alternative methods. But at present, only partial replacement methods are available, which can be used to partially identify non-classified chemicals and or chemicals seriously damaging the eye. None of these methods can currently be used on its own to directly identify in vivo category 2 chemicals. To better understand the reason for this, ECVAM, in collaboration with Cosmetics Europe and Else Adrians, performed an in-depth analysis of historical in vivo rabbit data. The main objectives of this study were to identify which endpoints are most important in driving GHS classification for serious eye damage or eye irritation, and to evaluate the Draize within test variability in order to propose acceptable and realistic target values for false negative and false positive rates for alternative methods. Next slide, please. I will only shortly present the conclusions of this study in this webinar, so for more details I strongly advise that you take a look at our publication from earlier this year, which is available in open access and can be downloaded using the link provided in the slide. Next slide, please. So, in this study we evaluated historical in vivo data coming from four different sources. The first 3 represent reference chemicals databases that were developed mainly to support the validation of alternative methods. These databases were pooled and analyzed together, and most of you are probably familiar with them. The CTOC database, the ZVAP database, which was used in the validation of several methods by BFR in the late 90s, and the database from Laboratoire National de la Santé, which was used in the initial validation of the BCOP test method by Gauthieron. The fourth source was the European New Chemicals database, which was maintained by the former European Chemicals Bureau and contains all chemicals registered in EU by multiple industry sectors since 1981. The table in this slide shows the distribution of GHS categories in both databases. The RCD, the reference chemicals databases, contain significantly more classified chemicals than the NCD, and also more category 1s than category 2s, which is not observed in the NCD. The distribution observed in the NCD is expected to represent more closely the prevalence of category 2 and category 1 chemicals in the chemical world than what is observed in the RCD, since, as I already mentioned, the NCD contains all chemicals registered by multiple industry sectors since 1981, while the RCD contains a limited number of chemicals that were put together mainly to support validation studies. What is clear from this table is that the biggest impact on animal replacement will come from alternative methods able to identify non-classified chemicals. Next slide, please. So, when we looked at the different in vivo drivers of classification, we could conclude that iritis rarely drives the classification of chemicals on its own. When iritis occurs, it is usually accompanied by other effects, mostly corneal opacity. So from this, we conclude that there is no need to specifically address iritis in vitro. Corneal opacity and conjunctival redness are the only important endpoints in driving a category 2 classification in vivo, since together they account for more than 90% of the classifications. Like iritis, chemosis also rarely drives a category 2 classification on its own, and it's in less than 2% of the cases. In 10 to 20% of the chemicals, corneal opacity drives classification on its own. But for almost the double of that, conjunctival redness is the only endpoint driving classification. Therefore, in vitro methods must be able to identify not only corneal opacity, but also conjunctival redness in order to avoid false negative results. And this is an important point since, as most of you probably know, the majority of in vitro methods that have been developed and are available mimic corneal tissue. Finally, when it comes to category 1 chemicals, we observed that the majority were classified on the basis of persistence of effects at day 21, but with mean scores of days 1 to 3 below the category 1 classification threshold, while only about 30% of the category 1 chemicals showed enough severity in the first 3 observation days to generate the classification. 80% of the category 1 chemicals showing only persistent effects had persistent corneal opacity. The remaining 20% were classified mostly on the basis of score 1 conjunctival effects at day 21, which should probably not even be classified as category 1 in the first place. GHS currently considers full reversibility as 0 scores for all endpoints. But for instance, the US CPA classification considers conjunctival scores of 1 as fully reversed, which actually makes more sense since the classification cutoff is a score of 2, not of 1. Based on this analysis, we concluded that it will be necessary to have alternative methods able to distinguish between persistent and reversible effects in order to achieve full replacement of the animal test. Again, this is quite important since the majority or the great majority of the methods available look at immediate effects and they are not developed to address persistence. Next slide, please. We also explore the influence of within-test variability on GHS chemical classification using a statistical resampling technique. This slide summarizes the procedure we applied using non-classified chemicals as an example. Basically, we have 1,537 non-classified chemicals in the new chemicals database, which were all tested in 3 animals. This provided us a pool of 4,611 animals, from which we sampled 3 animals 10,000 times to derive 10,000 theoretical classifications. We then looked at the distribution of those 10,000 classifications. And as you can see from the second table in this slide, almost 100% of the theoretical chemicals were not classified, which means that the within-test variability of the Draize eye test for non-classified chemicals is quite low. We also did the same resampling for the category 2 and the category 1 chemicals in our databases. Next slide, please. The conclusions from this analysis are that the overclassification error of the Draize eye test for non-classified and category 2 chemicals is negligible. However, at least 12% of the category 2 chemicals could be equally identified as not classified in a repeated test, and at least 11% of the category 1 chemicals could be equally identified as category 2 in a repeated test. Importantly, these probabilities only account for within-test variability, and therefore They may certainly increase if between laboratory variability would be considered. The resampling results also suggest a high overpredictive power of the Draize eye test using the current classification criteria, because the distributions are always skewed significantly towards lower classifications and never to higher classifications. And the main contribution for this is the fact that category 1 classification based on persistence of effects usually or is obtained with one single animal, a single persistent endpoint in one single animal, independently of the number of animals of the study. So obviously this is a very conservative approach, and that leads when resampling to only lower distributions and very seldom to higher distributions. So in conclusion, these findings should be considered when defining acceptance levels of false negatives and false positives in the development and validation of alternative methods and testing strategies. Next slide, please. In the field of serious eye damage and eye irritation, it is currently agreed that no single in vitro method will be able to fully replace the animal test for all types of chemicals and across the entire range of in vivo responses. Instead, combinations of several in vitro methods into testing strategies will be necessary. Next slide, please. A conceptual framework of a testing strategy for serious eye damage and eye irritation was developed in 2005 in an ECVAM expert meeting. Basically, depending on the physicochemical properties and the anticipated degrees or irritation of the chemical, a so-called top-down or bottom-up approach is initiated. If a chemical is expected to induce irritation or damage in the eye, a top-down approach is used with the chemical being first tested with a method showing a low number of false positives when distinguishing category 1 from the rest. If the chemical is identified as category 1 in the first year, it is classified accordingly and no further testing is required. If the chemical is identified as not being category 1, it would then be tested in a second method showing a low number of false negatives when distinguishing non-classified chemicals from the rest. If the chemical is identified as not required classification in the second tier, no further testing is required. Otherwise, further testing would be necessary, or a default category 2 classification could be considered depending on the characteristics of the methods used in the first years. The bottom-up approach works in the reverse order, starting first with a test method able to identify non-classified chemicals with a low rate of false negatives. So a method that can be used for both identifying category 1 chemicals and chemicals not requiring classification for serious eye damage, eye irritation, is characterized by two sets of accuracy values, basically two sets of false negatives and false positives. And you can see that from the schemes on the right-hand side and left-hand side of the slide. So for methods to identify category 1s, you have false negatives identified as the category 1s that are underpredicted as 2s or no categories. And the false positives are identified as category 2s or no cats that are identified as 1s. On the other hand, for bottom-up, to identify no category, false negatives are determined by 1s and 2s that are underpredicted as not classified, while false positives are determined as the not classified chemicals that are overpredicted as 1 or 2. I will now hand over to Kim, who will present the currently available alternative methods. Kim?
Hello, Gilly. Over to you. Thank you. You just need to unmute your microphone, Gilly. Oh, Kimberly. Over to you, Kimberly. Thank you.
Thank you. So thank you, Joao, for that introduction, and Gilly. The alternative methods can be grouped according to the nature of the test system, beginning here with the organotypic assays, which are based on isolated eyes or corneas, or based on the chicken egg Chorioallantoic membrane. The main examples are listed here, which include the Bovine Corneal Opacity and Permeability Assay, the Isolated Chicken Eye, Isolated Rabbit Eye, and the hen's egg test on the Chorioallantoic membrane, or HET-CAM. Secondly, the cytotoxicity and cell function-based assays, including fluorescein leakage, Cytosensor Microphysiometer, and short-time exposure. Next, with the reconstructed human tissue model, under that category is the EpiOcular eye irritation test, or EIT, and lastly, the in chemico assays, and listed here is the Ocular Irritation assay. Next slide, please. I would also like to point out some of the software tools with functionalities for predicting eye irritation potential. These include ToxTree, OECD QSAR Toolbox, Derek Nexus, TopCat, MolCode QSAR Model, and Multicase. The freely available ToxTree and OECD Toolbox include the BFR rule base, which applies a set of physicochemical rules to predict the absence of effects, along with a set of structural rules to predict the presence of effects. All of these tools may be used in a weighted evidence approach or in a tiered testing strategy to inform you on your eye irritation labeling. Predictions should be evaluated using information on the model characteristics, and for classification and labeling, the BFR rule base provides information that is closest to the regulatory goal, as the system was designed to predict the then EU risk phrases for eye irritation. Next slide, please. For a mechanistic understanding of the endpoint of eye irritation, we should consider the common modes of chemical action in ocular toxicity, including cell membrane lysis, where surface active agents may solubilize membrane lipids, and organic solvents may extract lipids, protein coagulation and denaturation, and also including precipitation, most likely caused by contact with acids, alkalis, and certain solvents, saponification, or the alkaline hydrolysis of lipids, where the effect is often progressive, and chemical reactivity, or those chemicals reacting with cellular macromolecules. A particular concern of these chemicals because of their delayed onset of damage, and these may include bleaches and peroxides. And here on the left we have an image of a cross-section of a human cornea, and I'd just like to point out some of the key characteristics, being the 1, epithelium, 2, showing the Bowman's layer, 3, the large portion of the stroma, 4, the Descemet's membrane, and 5, pointing out the thin layer of the epithelium. Next slide, please. The BCOP assay, or Bovine Corneal Opacity and Permeability Assay, is a test system which uses corneas which are isolated from bovine eyes obtained from abattoir animals. On the picture on the left, you can see a whole globe bovine eye which is received into the laboratory, and then the cornea is removed from that eye. There are 2 objective endpoints measured in this assay: the corneal opacity, or the passage of light through the bovine cornea, and permeability, as quantified by the amount of fluorescein dye that is able to pass through the cornea, the full thickness of the cornea, from being applied onto the epithelial surface. The protocol varies depending upon the nature of your test substance, with liquids being applied neat and surfactants and surfactant mixtures being applied onto the cornea at a 10% dilution. And they're exposed to the corneas for 10 minutes with a 2-hour post-exposure incubation. The solids are diluted 20% in an appropriate solvent and exposed for 4 hours with no post-exposure incubation. The assay is validated and regulatory accepted for identifying GHS Category 1 and no category, but not currently for Category 2. And the OECD test guideline is 437. The assay may be also used in the US EPA program to identify Categories 1 and 2 for eye irritation. A few points on the applicability and limitations of the assay according to the test guideline. For the no category, there may be a high level of false positives in general. For Category 1, there is a high false positive rate for alcohols and ketones, and that's using the standard 10-minute exposure. And we found that the 3-minute exposure may better model eye irritation for these test substances. And there's also a high false negative rate for Category 1s for solids, but relating back to Joel's talk, many of those are false negative for chemicals which are based on persistence without severity. I would also like to point out here this link on the tutorial on the BCOP assay. This link is a link to a training video on the BCOP assay, which was prepared in collaboration with the European Partnership for Alternative Methods and IIVS. This video details all of the steps of the assay and is freely available on the EPA website. Next slide, please. I would also like to point out that histopathology may be used on such organic type models as the rabbit eye, bovine eye, and the chicken eye to obtain more information. It may be used to obtain more information on both the degree of damage and the depth of penetration. It also may improve the prediction of chemicals inducing persistent effects without initial severe damage. In this figure, I would just like to point out these are cross-sections of bovine corneas which were tested in a BCOP assay. And the image on the left shows a control cornea, and then the image in the middle is showing a cornea which has been treated with a low level of SLS, which is a surfactant, for a 10-minute exposure. And you see here sort of a progressive damage across the epithelium of this cornea. And then in the image, the third image, you'll see with a higher amount of SLS, you see more damage to the extensive damage to the epithelium and a complete detachment from the basement membrane and a disorganization of the stroma. Next slide, please. The isolated chicken eye assay, the test system is chicken eyes isolated from abattoir animals, and the endpoints are measured are corneal opacity, fluorescein retention, corneal swelling, and morphological damage. In the protocol, test chemicals are exposed neat for 10 seconds and assessed during a 4-hour period. Currently, this assay has an OECD test guideline 438, and it may be used to identify category 1 and no category, but like the BCOP, it's not able to label for category 2. A couple of the applicability and limitations for ICE as identified in the test guideline. Once again, there's a high false positive for alcohols and false negative for solids. And the third point I'd like to point out here is, although there is this high false negative for surfactants, histopathology was shown to improve prediction for non-extreme pH detergent and cleaning products in a recent publication. Next slide, please. The isolated rabbit eye test uses rabbit eyes, which may be isolated from abattoir animals or animals which are used for other testing purposes. The endpoints measured are the opacity, corneal swelling, fluorescein penetration, and assessment of epithelial integrity. Two of those which can be seen here on the left, the opacity and the fluorescein penetration in those images where you see progressive damage across those corneas. For the protocol, the liquids are applied as 0.1 ml onto the center of the cornea for 10 seconds, and solids are applied as 0.1 grams. They're sprinkled over the cornea for 10 seconds, and the test materials after that short period are then rinsed and monitored at various times over a 4-hour observation period. Currently, the assay has been evaluated in several international validation studies and may be used for identifying GHS Category 1. However, there is not a draft test guideline for this assay that has been submitted to OECD. The assay is applicable to a broad range of test substances, but like the other models, it is not able to assess reversibility of the corneal lesions. Next slide, please. The hen's egg test on the Chorioallantoic membrane, or HET-CAM, uses chicken eggs which are at the 10th day of embryonation, as shown here on the left. In the assay, coagulation and hemorrhage and lysis are measured to identify either the category 1 or no category. For the protocols, for a category 1 assay, you're looking at the time to develop effects during a 5-minute exposure. And for the no category protocol, the effects are observed at different fixed time points of 0.52 and 5 minutes. This assay was validated by exam but was not recommended, and as it needed more data to make further conclusions. However, I would like to point out that an international workshop was held in 2012, and this assay is currently undergoing additional validation. An important point here for the applicability of this method is that it is the only method which is directly addressing those conjunctival effects, which we know are important as relayed by Joao in his introduction. In terms of the limitation, chemicals that affect the membrane or the readout, such as sticky materials, colored materials, and those materials which cause a physical abrasion, may be incorrectly predicted, and along with alcohol. Next slide, please. Now moving into those cell-based assays. The fluorescein leakage assay uses the MDCK tubular epithelial cells, and it's measuring a trans-epithelial permeability to fluorescein. And you'll see here the image on the left of the inserts and the cells. In the protocol, the test system is exposed for 1 minute to various concentrations, followed by a 30-minute incubation with fluorescein. Currently, this assay has an OECD test guideline, 460, and it may be used to identify category 1 only. In terms of the applicability and limitations, it is only applicable to test chemicals that are soluble or that form a stable suspension at specified concentrations. The assay is not applicable to those strong acids and bases, cell fixatives, or highly volatile chemicals. And colored and viscous chemicals may be wrongly predicted. Next slide, please. The Cytosensor Microphysiometer, as shown on the left, uses a subconfluent monolayer of mouse L929 cells. It's measuring the cellular metabolic rate, or the rate of acidification. These cells are exposed progressively to increasing concentrations of a test chemical at a 13.5-minute exposures, followed by a rinse out and then a 25-second metabolism measurement. This assay is currently validated and recommended for identifying UNGS category 1 for those aqueous soluble chemicals, and no category for aqueous soluble surfactants and surfactant mixtures. Like many of the cell-based assays, there will certainly be a limitation for solubility, and so you have to have water miscible solvents, or they must form a stable suspension at specified concentrations. Next slide, please. In the short time exposure test, a confluent monolayer of circ cells are used to simply measure the cytotoxicity using a very short time exposure of 5 minutes. And the test chemicals are exposed at 5% and 0.05%. And currently, this assay has an OECD test guideline under discussion, and it's been validated and recommended for identifying GHS category 1 and no category. For no category, there is a high false negative rate for highly volatile chemicals with a certain vapor pressure. And for category 1, there is incidence of high false negatives in general. And once again, since it's an aqueous-based assay, it's not applicable to test chemicals that are not soluble or do not have a form of stable suspension. Next slide, please. Next, we'll move into the reconstructed tissue models here. This is an example, the EpiOcular model, which has an eye irritation test, or EIT. In this test system, a non-keratinized multi-layer epithelium reconstructed from primary human epidermal keratinocytes are used to model the corneal epithelium. These tissues are manufactured by Matec. The protocol, we're going to measure cytotoxicity using NTT, and the protocol for liquids is that they're exposed for 30 minutes, followed by a 2-hour post-exposure incubation. And for solids, they're exposed neat for 6 hours, followed by an 18-hour post-exposure incubation. Of note, the solids protocol was optimized during the validation study, and the sensitivity was greatly increased with that change. And the status for this assay is that it's been validated and recommended for identifying UNGH no category, but not able to distinguish between category 1 and category 2 currently. And a draft OECD test guideline is currently under discussion. The assay is applicable to a broad range of chemicals. However, intensely colored materials may need to have an additional endpoint to be addressed with HPLC for additional clarification. Next slide, please. In addition to the EpiOcular model, I just wanted to briefly mention that there are certainly other models that are developed, one of them here being the human corneal epithelium model. And in this test system is a multi-layered epithelium prepared from immortalized human corneal epithelial cells. Briefly, the assay is generally similar to EIT in that you're looking at MTT and cytotoxicity as your endpoint. Currently, this assay is not considered valid due to a poor sensitivity. However, it had a high reproducibility, and it's undergoing additional optimization and external validation by the method developer. Next slide, please. The ocular irritation model is an in chemico method where the test system is a macromolecular matrix which is composed of lipids, glycoproteins, carbohydrates, and other components which are integrated to mimic the highly ordered structure of the cornea. We're measuring the turbidity at a certain wavelength, and in the protocol, the test system, it has a 24-hour exposure to varying amounts of chemical, and then you use a specified protocol depending upon the nature of your test substance, whether it be a surfactant or not. Currently, this assay has undergone an external validation and now being evaluated by exam for identifying category 1 and no category. The assay is fast and simple, and you have a 2-year shelf life on the kit that is sold. But there, of course, are some limitations with what chemicals are applicable to the assay. pH is important for those chemicals which may be excluded. And there are certain mispredictions with certain chemistries, as noted here. Next slide, please. Moving on from the methods which I initially discussed, I would like to just simply point out here that these are some of the methods under development to assess the endpoint of persistence, which is lacking currently in the models that have been developed. So there are some kind of some assays currently undergoing some additional validation. I just want to discuss those here, including the ex vivo eye irritation test, which was developed by the University of Aachen in Germany. This assay uses X-sized rabbit corneas, and it monitors full-thickness corneal recovery over 3 days using an optical coherence tomography, following a 60-minute exposure to solids or 30 to liquids. Next is the porcine cornea ocular reversibility assay, or PORCORA, which is developed by MB Research Laboratories. This assay uses a porcine cornea, and it monitors epithelial recovery over 20 days by fluorescein stain retention following a short exposure. Lastly, I'd like to point out the method of using the initial depth of corneal injury assessment to monitor or assess persistent effects, developed by James Maurer and Jamie Jester. And in this model, they propose that the initial depth of injury is predictive of the degree of damage and duration of injury to the cornea, and the cornea is evaluated by histopathology and also live dead staining. Next slide, please. In this slide, this is just a simple overview of those things that I have presented thus far, with those in green showing the assays which may be used to assess no category, and those assays highlighted in red may be used to assess the category 1. And here we see in the middle for GHS2, there's currently no assay listed there, but Joao will discuss with us the use of testing strategies to assess GHS2 and how all of these assays may be used for submission to REACH. Next slide, please. A couple of practical considerations when you're developing your testing program. First of all, most importantly, to determine is your sample being tested for regulatory classification and labeling. If it's not, you may use other approaches for product development or screening purposes. You may use assays that I haven't presented here today, or you can use the assays I have presented, but perhaps with different protocols. And if it is to be tested for regulatory classification, then if so, what is the most appropriate assay system and what is your guidance? So you may want to consider the following, including your physicochemical properties, solubility, and if you're working with an ingredient or formulation, and if it's in a formulation, what components of that formulation may be likely to cause eye irritation. You want to explore the availability of the selected methods to ensure proper assay performance, and then prepare the appropriate protocol, which is adhering to the OECD guidance for your selected test method. You want to also ensure proper training on the method, whether you're bringing the method in-house or you're contracting out before conducting the routine testing. And for each submission, you're going to want to conduct those assays under good laboratory practice compliance using all the controls and assay acceptance criteria as outlined in those test guidelines. And concurrently tested benchmarks or reference samples may also be useful. And I believe that concludes my portion, and now I'll turn it back over to Joao for additional discussion. Thank you.
Thanks, Kim, for this excellent presentation of the available alternative methods for eye irritation. So I will now try to briefly explain how the various in vitro methods that were presented by Kim can be used under REACH. REACH Annex 7 and 8 define the standard information requirements for serious eye damage and eye irritation. Annex 7 defines the standard requirements for substances manufactured or imported into EU in quantities of 1 to 10 tons per year, and Annex 8 defines the standard requirements for substances manufactured or imported into EU in quantities of 10 or more tons per year. As you can see, in vitro methods are already a standard information requirement under Annex 7 and therefore need to be performed to assess the serious eye damage, eye irritation properties of a substance. On the other hand, the standard requirement under Annex 8 is currently the in vivo Draize eye test. However, since the annexes are cumulative, a registrant should nevertheless perform in vitro methods to fulfill the requirements of Annex 7 before considering an in vivo test under Annex 8. Next slide, please. It should also be mentioned here that the Commission has recently proposed a revision of these two annexes to the EU member states, where in vitro methods become the only requirement under Annex 7, and an in vivo study under Annex 8 can only be considered if it is demonstrated that the available in vitro methods are not applicable or are not adequate for classification. If the proposal is approved by the member states, these annexes may be revised during the course of next year. However, to fulfill the requirements of Annex 8 with in vitro methods, a registrant currently needs to submit the data as an adaptation of the standard requirement and provide an accepted waiving argument. Next slide, please. Oh, it's okay. It's this one. So, no, previous slide. Thanks. So, Annex 11 describes the general rules for adaptation of the standard testing regime set out in Annex 7 to 10. Point 1.4 of this annex regards the use of in vitro methods and describes the waiving arguments that can be used for adapting the in vivo study requirement of Annex 8 with in vitro methods. In vitro methods that have not yet been validated but that are sufficiently standardized can be used to identify positive results. Negative results obtained with such suitable methods would still need to be confirmed with an in vivo test. However, scientifically valid methods may also be used to identify negative results, and therefore the provisions of Annex 11 allow for the replacement of the in vivo test for serious eye damage and eye irritation, since, as explained by Kim, there are already several in vitro test methods that are considered scientifically valid to identify non-classified chemicals, and some of those have already been adopted as test guidelines by the OECD. Next slide, please. An important document that should be consulted before generating data for fulfilling REACH requirements for serious eye damage and eye irritation is the REACH Guidance on Information Requirements and Chemical Safety Assessment, Chapter R7A, Section R72 on Irritation Corrosion. This document provides a guidance on how to fulfill REACH information requirements using different types of information, including alternative methods, and includes a general integrated approach to testing and assessment, which can be very helpful in structuring data collection and data generation where required. This guidance is currently being updated to accommodate the various new test guidelines and guidance documents that have been published in the last years. This update can be followed through the link provided in the slide. The European Commission and the US have also jointly submitted to the OECD a new project proposal for the development of a guidance document on an integrated approach to testing and assessment for serious eye damage, eye irritation. So more developments to come in the near future in this area. The OECD will decide on the approval of the project proposal in April next year. Next slide, please. Other official documents summarizing the available in vitro methods for serious eye damage and eye irritation are shown in this slide, and can be downloaded using the links provided. I strongly recommend the read of the state-of-the-art review on alternative methods that we have produced for ECA and that was recently published. Next slide, please. So I move now to the last part of this webinar. This table shows the accuracy values of the various in vitro methods that can be used or have been proposed to identify non-classified chemicals. You can see that all these methods are characterized by a very low rate of false negatives. The values in brackets correspond to the accuracy values calculated when removing chemicals out of the applicability domain of the methods. However, all these methods are characterized by a significant number of false positive results. That means non-classified chemicals that are identified as positives. Amongst these, the ones that show lowest false positive rates are the isolated chicken eye, the EpiOcular irritation test, the short time exposure, and the ocular irritation. All these false positive results would require further testing if following the bottom-up strategy. So after the first year, they would be identified as positives, and they would require further testing. Next slide, please. So from the slide before, you can see that one should start a bottom-up approach with one of the methods showing lower false positive rates. That is the EpiOcular, the isolated chicken eye, the ocular irritation, or the short time exposure, taking into consideration to their applicability domains and their limitations. One important aspect that I would like to mention here is, I mentioned in the first part of my talk that conjunctival effects are quite important and they would need to be addressed in vitro. And none of these methods, maybe apart from HET-CAM, apparently addresses conjunctival effects directly. However, from the validation of all these methods and the very low false negative rates, you can already see that chemicals that are classified in vivo based only on conjunctival effects are actually not underpredicted by these methods. So in fact, although we need to address the endpoint, so far from the available data, none of these methods seem to have a specific limitation in correctly identifying chemicals that are classified based on only on conjunctival effects. Now, 60 to 80% of the non-classified chemicals should be identified with a single method and with less than 5% false negatives. So already here you can see that, and also taking into account the prevalence of industrial chemicals that are presented in the beginning of the talk, you can already see here that for the great majority of the chemicals you would be able to come to a conclusion on the basis of a single method. In some cases, more than one method will be needed. And this, of course, in case you obtain a positive result in the first year. And you would need to do further testing in order to decrease false positives. But because all these methods are characterized by very low false negative rates, you can actually combine one or two or three, and you will increase the number of correctly identified negatives without really an important impact on the false negatives. Moreover, most methods can be used to identify both category 1 and no category. And this, of course, increases the efficiency of the strategy, because with a single method you can actually identify both ends of the scale. Next slide, please. So now this table here presents the predictive capacity of the various methods that Kim described, but now for the identification of category 1 chemicals. And you can see that all these methods are characterized by rather low rates of false positives. That is, chemicals that are not Cat1 but that are identified by the methods as category 1. And conversely, they have, some of them, significant rates of false negatives. So chemicals that would then require further testing after the first year if you follow a top-down approach. What is interesting is that most of these false negatives are coming from chemicals that are classified based on persistence of effects only, without severity in the first 3 observation days in the Draize test to generate the category 1 classification. Next slide, please. So now, based on those values, it is clear that one should start at the top-down approach with one of the methods showing lower false negative rates, and that would be the Cytosensor Microphysiometer or the Bovine Corneal Opacity and Permeability test, or the isolated chicken eye if you are testing surfactants and you are coupling the method to histopathology evaluation, like mentioned by Kim earlier. 15 to 50% false negatives, which are under-predicted category 1 in each of these methods. So you obtain about 15 to 50% false negatives in each of these methods. And these are mostly chemicals that are classified in vivo based on persistence without severity. However, as Kim also explained, there are already some methods available, non-standard methods, non-validated methods, but in vitro methods, that can be used to address the persistence of effects and persistence versus reversibility. And I note here Evite and Porcora. And you should remember, as I mentioned before, according to Annex 11, you can use non-validated methods that are sufficiently standardized to identify positives. So if you actually use one of these methods to identify persistence of effects to clarify a category 1, you are certainly able to do that under REACH. Now, so if you do that, if you address persistence of effects and you can actually increase the coverage in the detection of no category and category 1 by a combination of more than one method to identify non-classified chemicals and methods to identify persistent, you could actually increase the confidence in the default category 2 classification in the last year. I note again that this would be the minority of the situations, because as I explained before, in the majority of the situations you may be able to identify a chemical with a single test. But if you are not able to do that, if you address persistence and you combine more than one method to identify negatives, you actually may be able to justify a default category 2 classification in the last year. Next slide, please. So to conclude this talk, I would like to mention the following point. So as I explained before, in vitro methods are the standard information requirement under REACH for substances produced between 1 and 10 tons per year. For substances produced between 10 and 100 tons per year, the in vivo test is currently the standard requirement, but this can be adapted with use of in vitro methods using the provisions of Annex 11.1.4. It is estimated that at least 70% of the substances, for 70% of the substances, one single in vitro test method will be sufficient to derive a final conclusion on serious eye damage, eye irritation, if the method is carefully chosen. For 20 to 30% of the substances, a combination of 2 or more methods may be needed. And importantly, full replacement may be achieved in the majority of cases if due consideration is given to persistence versus reversibility. And I conclude here the talk, and I open the panel for questions. Thank you.
Thank you very much indeed, Hal, for that talk, and thank you also to Kim. I think, yes, we should open the questions. We have quite a few of those. Firstly, to go back towards the beginning of the talk, so I guess this will be for you, Hal. How could in vitro tests be used to justify specific concentration limits for substances to be used for calculation by the additivity methods?
Yeah, I think that question came up also in the skin irritation and corrosion webinar, if I recall. I cannot give a direct question. I think they can be used, but honestly, I would not know how. I don't know, Kim, do you have any idea on how to reply to this question?
No, I don't think I have anything further.
So what I propose is that I will check in and maybe provide a reply written at a later stage, if that's okay.
Okay, we'll leave it there for now. To take another question then, In the validation of in vitro methods, the Draize test is used as a basis, but how well does the rabbit eye predict the human response with respect to eye irritation?
So I can start with that. I mean, for eye irritation, the situation is a bit more complicated than for skin irritation, for instance, because in skin irritation we do have some high-quality human patch test data that have been used to compare to the Draize skin data, and they actually have been mentioned in test guideline 439 on skin irritation. And from there, it's clear that the Draize test is more towards over-predicting the human situation than under-predicting it. For eye irritation, there is no, as far as I know, no really good high-quality human data, and most of the evidence comes from accidental exposure. Still, it is from the available evidence, it's clear that the Draize test rather over-predicts the human response, also from the nature of the test itself, because exposure in the Draize is maximized. In the older studies, there was no washing permitted, and solid materials sometimes stayed in the eye for very long periods of time, which obviously exacerbated the responses, and many times delayed effects could be seen due to secondary infections coming from just abrasion and not really a direct chemical action. Also, the interpretation of the Draize data using GHS criteria, as I explained before, is quite stringent, which certainly would lead to overclassifications. Nevertheless, the Draize test is the regulatory method, and when trying to implement alternative methods, we are always faced with direct comparison with the Draize. And therefore, it was important to analyze exactly the limitations of the Draize and analyze what we can obtain from the Draize so that we can facilitate future replacement.
Thank you. Can we now turn perhaps to Kimberly? There's a question here. Does the globally harmonized system recognize the ICA, the isolated chicken eye assay, for classifying eye irritation?
Yes, under UNGHS, you could use the ICE assay to classify severe eye irritants category 1 or no category based on the scores in that assay. But you can't use for the category 2.
Okay, well, that's a clear answer to that question. This is probably for Hal, this question. We recently had to submit, the questioner asked, we recently had to submit samples for several eye irritation and damage tests when working with a consultant in Germany developing global harmonized system compliant safety data sheets for the EU. Do these tests have to be performed in the EU as opposed to the US to be considered valid?
So I'm not sure if I understood correctly, but methods that are accepted in OECD guidelines, basically results obtained with those methods should be accepted across the globe because they are covered by mutual acceptance of data. Of course, all these methods that Kim described are mainly applicable to GHS, but actually BCOP and ICE are also accepted for once for EPA, US EPA for instance, not necessarily for non-irritants because there the GHS and US EPA classifications differ a bit. Some of the UNGHS not classified chemicals are classified under US EPA as category 3, so the methods do not work exactly the same way for GHS and US EPA. But for once certainly they can, and the US EPA has also a strategy accepted for antimicrobial cleaning products that uses BCOP, Cytosensor, and EpiOcular, although using a different EpiOcular protocol using time to toxicity. I'm not sure if this was exactly the question. In order to generate information for MSDSs, I guess, yes, the methods should be accepted for that. I don't see any reason why not, since usually in MSDSs the classifications provided are GHS.
Okay. Thank you for that answer. Another question here to the panel, I think. There's a large number of possible test methods for in vitro test methods. Guidance and annexation mention appropriate. Guidance and the annex mention appropriate tests and general points, but it's very hard to conduct the right test. Is there further guidance on the usage and methods available, or at least planned? So which methods do you choose, basically?
Yeah, Kim, go ahead.
I can take that. Just to begin, that's why I had I know we presented a lot today and a lot of different methods on the slide with the practical considerations. We'll kind of go through that checklist first to really think about what are the physicochemical properties of your sample, and then to go through and decide which assay is the best assay based on just the limitations of each of the assays. And then once you've selected those assays which are most suitable for your test material, then you can explore the availability of those methods and make a decision whether you can speak to a reliable contract lab and see if they can perform that assay, or you consider bringing the method in-house. And you need to, always ensure proper assay performance. But I think if you go generally from that perspective, you should be able to pick an assay which suits your test materials and your end goal based on what are the characteristics of the test sample and which category are you intending your sample to fall in, be it a no category or perhaps a GHS1.
Okay. Perhaps a couple of important questions here. Are these tests applicable to nanomaterials, and have they been used for such?
Well, very good question. Well, the question of nanomaterials is obviously coming up now. As far as I know, well, certainly in validation studies, not yet. So, I mean, they may have been used, I'm sure they have, but by specific companies or industries. But no data that I personally have seen. The question of nanomaterials is coming up at the WMT level, at the OECD, and certainly people are starting to discuss the applicability of the various methods to nanomaterials. And one of the first cases is genotoxicity, where, for instance, discussions are going on the applicability of the micronucleus test to test nanomaterials. So far, the approach of the OECD has been that nanomaterials could in principle be tested, and the approach is similar as the one taken for mixtures. They can be tested unless proven contrary. But the question with nanomaterials is much more complex, and therefore I think this will have to be addressed in the near future, basically on one method at a time and on a case-by-case basis. But in principle, with nanomaterials, mostly the question is about characterizing well what's being tested under the test conditions, because the actual form of the chemical under testing becomes crucial, especially in methods that are done under solution conditions.
Okay. Here's a very quick question, probably a long answer. What are the average costs of these tests, in vitro tests? Can anybody answer that one?
Kim, do you want to take that one?
Sure. I can give some general guidance on that question. So as compared to the Draize test, I would say that these assays that I presented are generally in the same range as that test. It may be more expensive, but of course it's going to depend on your testing needs. If you need the test done GLP, what are your requirements in terms of your reference chemicals and benchmarks? In general, these tests, since I'm in the U.S., I can mention in dollars, you may be looking at, around $1,000 to $10,000 for an individual test or a series of tests to assess a certain endpoint. But I would say certainly all of these assays are within a similar range to each other for the ones I presented, although you're going to have some differences based on the model you're using. And they're also within the same range as testing with the Draize test. But for specific testing information, I would rely on talking to your contract labs or a consultant, or determining how much it would cost for you to bring the assay in-house and run on a per chemical basis.
Okay. Okay. Kimberly, a question specifically aimed at you by the questioner. I mean, how can in vitro or in silico approaches address chemicals that are not classified because conjunctival redness or chemosis and lesions subsequently disappear in the Draize test within the observation time?
See, that one may have a challenging answer. May have Joelle join in, but certainly with the in vitro methods there are currently methods, including the BCOP assay and the ICE assay, which can be used to label no category, or essentially non-irritating. So those assays currently may be used to label, or I guess the absence of labeling, for a category of eye irritation. Furthermore, as Joelle mentioned, for the HET-CAM assay, that's the only assay that's really been clearly identified to assess those conjunctival effects. And I'm assuming we'll kind of begin to learn more and more regarding the testing strategies. But currently, we do have two assays that can be used for the no category.
Yeah, I can add to that just to say that, for instance, in the validation of the EpiOcular and the SkinEthic, during the chemical selection for the validation, we specifically selected chemicals that were classified based on the Draize, based only on conjunctival effects, and mostly conjunctival redness, but also chemosis. And all of those chemicals, all of them, 100% of those, were correctly identified by the EpiOcular, which is not surprising because conjunctival redness is mostly an inflammatory response, which is associated with cytotoxicity. And in the end, you're measuring cytotoxicity in the EpiOcular. I've also looked through the databases, the validation databases of BCOP and ICE, because those are also quite extensive. And also there, none of the chemicals that were classified in vivo based on conjunctival effects were mispredicted. So I mean, as I said in my talk, at the moment I don't see any limitation towards conjunctival effects. If the effects reverse, I mean, if they are low level, that they do not generate a classification, in principle, they are either correctly predicted by the methods or they are over-predicted. But there is no correlation, specific correlation on over-prediction specifically for these. They are as over-predicted as chemicals that are showing only corneal opacity. If they persist and would generate a Category 1 classification, then we are entering the discussion on persistence versus reversibility, which we have also covered in the talk.
Thank you. We are overrunning slightly, but there are just a couple more questions to ask. Perhaps I can ask them together, and then we can wrap up. There's a question here aimed particularly at Hao, which is to address the issue of mixture classification in eye tests. And the other one, the final question is, does anyone on the panel have any suggestions on which assays could be used to tease out category 2 compounds?
Okay, so I can maybe start with the first question, which was, can you remind me again?
The mixture classification.
The mixture, yes. So for BCOP and ICE, the methods were actually validated with several mixtures. They were included in the validation study, and both methods were found to be applicable to the testing of formulations. And they included several types of industrial formulations, not only cosmetic ones, but also from other sectors. In terms of the reconstructed tissues, EpiOcular, for instance, the validation study did not include mixtures because obviously the BCOP and ICE were validated by retrospective evaluation, and all their data were acquired in parallel with in vitro and in vivo studies. So formulations could be included several years ago. Nowadays, obviously, it's not ethical, and we would not be able to test in parallel in vivo, and therefore to include formulations in validation studies is quite complicated. But industry does have historical data on proprietary formulations, and for instance, at a recent expert meeting on irritation at the OECD, where the EpiOcular guideline was discussed, BASF presented recent data they have acquired on 100 agrochemical formulations that they have, for which they have Draize, historical Draize data that they tested in EpiOcular, and they obtained an accuracy of 80% and sensitivity and specificity almost identical to the ones obtained with substances in the validation study. So actually, from the data we have, it seems that the methods that are available are applicable to mixtures without problems. But of course, depending on the mixture or the product you want to test, you may have sometimes to adapt the protocol slightly. That will all depend on what you're testing and the specific characteristics of the formulation.
Okay. Anything to add to that, Kim?
No, I don't have anything additional for that.
Okay. And anything on the which assays should be used to tease out category 2 compounds?
Well, at the moment, there is no in vitro method adopted by the OECD or being proposed or being validated to directly identify category 2s. The Porcora and the Evite methods that Kim mentioned do allow for the identification of category 2s, but apart from persistence, of course, the biggest problem in identifying category 2s comes from the underclassification of category 1s based on persistence, because the overclassification of no categories of non-classified chemicals can be overcome by combining several methods, because the methods to identify negatives have so high sensitivities that you can combine 2-3 of them and you will not increase the false negatives, and you will end up probably identifying more than 90% of the negatives. But the persistency is still an issue. So these methods that are able to identify persistence to some extent obviously become also useful in identifying category 2. But you know, I think if people are able to identify persistence either by one of those methods or by other means, basically you will come to a situation where category 2 can be identified by default without the necessity to actually have a method to directly identify category 2.
Okay. Well, Kimberly, unless you've got anything more to say, I think it's time to wrap up. It's now 5:15. And I'd like to say a big thank you to both our speakers, well, all of our speakers, Gilly and Kim and Hao, and Thank you to all the delegates listening in to make this webinar such a success. I gather we have about 500 delegates signed up to this event, which is a good number. And I'd like to wish you all the very best of luck as you go about your work in this field. And thank you for listening in, and goodbye.